Hey everybody, good evening. Welcome. The topic for tonight is going to be patterns primarily, secondarily focusing on two related classes, streams and events. And I know on the syllabus it says what is it, like patterns, routines, tasks, clocks, scheduling, and well, frankly, I might have bit off a little more than I can chew because there's actually a lot going on here in terms of patterns and scheduling, and so we'll get to what we can get to. First, a quick sound check. Let me know if you're out there. Let me know if you can hear me, and let me know if you can hear my pink noise. Anybody out there? Let me know. Thank you, Schweide. Appreciate it. Hang on, my camera wants my attention. Okay. All right, so let's talk patterns. The resources, there's actually some documentation that I think is worth reading. Hey, Jungle. Hey, David. How's it going, guys? First of all, the corresponding tutorial is tutorial 10 on patterns. So in addition to the live stream tonight, I want everybody to watch this tutorial pattern, tutorial 10, because that's that's as usual, these tutorials are sort of more prepared, more concise, more to the point, and less rambly. And in addition, I just want to bring everyone's attention to the help documentation here. So if we go up to browse, and there's a category called streams, patterns, events. So we're going to be talking about patterns, but very closely related to this class, or this category of objects, are streams and events. So they're all sort of clumped together here. And at the very top, there is a series of documents called A Practical Guide to Patterns. And this first one is more or less a table of contents. It's written by H. James Harkins, who's one of the SuperCollider power users out there, who's sort of constantly answering questions on the listserv, and he's just an all-around SuperCollider wizard. So we'll do read the introduction, particularly the down here, why patterns, and we're going to sort of pull from this today a little bit. Patterns versus streams. Patterns define behavior, streams execute it. It's a nice summary right there. And there's also, if we go back a page, let's see if we, down here, there's a file. It's actually an overview file called streams. And this gives you the first page of the practical guide, as well as another series called Understanding Streams, Patterns, and Events, part 1 through 7. And this is also a very good guide about what streams are. So this first one is all about streams and what you can do with them. And part 2 is all about patterns and what you can do with them and how they relate to streams. So if you would, do take some time to read at least part 1 and 2 of Understanding Streams, Patterns, and Events, and take a look at H. James Harkins' Practical Guide. And there's a bunch of scattered help files throughout the Streams, Patterns, Events section. If you go to events here, there's also event and event types, and these have some useful information in them. Okay, so those are the resources I want you to check out, the tutorial 10 and these documents here. Let's dock that. Clear that. What else do I have on the table here? So first of all, what are patterns? That's a good question. Patterns are a class of objects which are fairly unique to SuperCollider. It's not, I mean, the ideas are found throughout other languages. I mean, it's not a radically new concept or anything, but essentially patterns provide high-level, somewhat abstracted, an algorithmic language, a high-level algorithmic language for sequencing data. And this data could be numbers, it could be sounds. It's a high-level language for creating a sequence of data. And a sort of weird irony, I don't know if it's exactly irony, but the idea of patterns, events, streams, and a lot of classes in general, these are very abstract concepts. They're very generalized ideas, but perhaps sort of weirdly, it's one of the most applicable areas of SuperCollider. It's really powerful stuff once you have a basic understanding of what patterns are, how they work, and where they're useful. So I guess I'd like to start by asking a question, like a programming question, which I don't really need an answer to, but you can all sort of think about it. How do we make a process in SuperCollider that gives us or returns to us an infinite arithmetic sequence, of integers? So the sequence 0, 1, 2, 3, 4, etc. Like, all the numbers. We just want to be able to say, give me the next number, give me the next number, give me the next number. And with the knowledge we currently have, something we might do, let's quit the server for a moment because we don't actually need it. Something we might do is make a routine. Or, yeah, I guess a routine makes some sense here. And I guess we can declare a variable, and we'll initialize it to 0. And then we make a loop. What we will do is we'll say number.postLN, number equals number plus 1, 1.wait, and end the loop, and play the routine. So this should give us, and it does, an infinite sequence of integers, simple arithmetic sequence. And this will just go forever, at least until it reaches the highest representable integer that the program can handle. Yeah, so that is one way we can do it. And since we've named our routine, we can say r.stop. And this is acceptable. We can improve on this. And I'm trying to build to the usefulness of patterns here. Something to notice here is that, okay, we have to declare a variable. We have to, we have to post it. We have to manually manage the incrementing process. And then, we have to wait for some period of time, and then we play the routine. So one way we can improve this is by first realizing that routine is actually a subclass of stream. Right? It inherits from something called thread, which inherits from stream. And let's look at the, let's go back to the, what was it, the overview here, and part 1. And we can see, let's zoom in a little bit, I guess. A stream represents a lazy sequence of values. The next value in the sequence is obtained by sending the message next to the stream. And we can scroll down a bit. Another useful subclass of stream is routine. Well, look at that. We've been using routine, and we've always been using it in a real-time sense. We've been saying .play and making sure to include wait times if we are looping indefinitely. And the routine just simply plays in real time and does what we tell it to do. So, but routine can be used in a different way. We can use, instead of saying wait, we can use yield. And in a play context, I believe this is synonymous. So Yeah, nothing has really changed here. Yield is in this context an alternative to wait, but yield doesn't just wait. It's not. I mean, why would you arbitrarily have two methods that do the same thing? It's a little bit different here. Let's comment out this. Let's delete number.postLn, and we'll put the yield up here. So that's the first thing that happens, but we're not going to yield 1. We're going to yield number. And now what I want you to do is don't think about yield in terms of a wait time here, because we're not going to use this routine in a real-time sense. We're going to use it as a stream. And when you have a stream, you can send it the message next, and it will give you the next value. And that's exactly what yield does. It's a point in the routine where the routine pauses and yields control to the process that's making the request, and it will give you the receiver of the yield message. So we're going to run this, and initially you might think, wait, we have no wait time. This is going to crash but we're not actually playing the routine. Notice that .play is gone. So now we can say r.next, and we get 0, right? Because what happens is we've made this routine, and then when we say next, the function inside the routine gets evaluated. So we have a variable, and we start looping, and we get to a yield. And the routine says, okay, I'm going to give you the receiver of yield. And so number, which is initially 0, is returned to us. And now we can call r.next again, and we get 1. And we can next, 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 next. And what happens is every time we call next, the routine picks up where it left off. It adds 1 to number, and it gets to the end of the loop, comes back to the top, and yields again, and yields again. We can even do r.next capital N. This is a different method, and then ask for a certain number of values. And this gives us an array containing the next n values. So we left off at 7, so now we get 8 through 17. Those are the next 10 values. We can do it again and again and again. And we can just grab these numbers as many times as we like. If we ever want to start again, we can say r.reset. And now if we do next n, what do you think we're going to get? We're going to get 0 through 9, right? Because we have reset the stream. Technically it's a routine, but routine is a subclass of stream, and we're using the next and reset messages that are defined for stream. So this is a little bit of an improvement. Of course, we could always, make another routine. And here we can say, well, let's reset that stream, and we will loop and say r.next.postln 1. Let's do 0.2.wait. It's a little bit faster here. So now we can play this one. And so we're sort of using one stream here, which gives us an infinite series. And then we're just calling next and posting the result 5 times a second. Okay, so the point of that is just to show you that routine is not just a real-time function that you can just play and you wait and do things. You can use it that way, but you can also use it in a non-real-time sense where you tell it specifically when you want it to advance and give you the next value. Right. And actually that's sort of what's going on here. We make a routine, and then instead of doing a loop, an infinite process, 3 times, we pass in the arguments, so 0, 1, 2, and we yield the result. Okay. Right. So let's move on and build on this. Okay. So even this is, good, but it's kind of a, it's still like, it's like 9 lines of code that we have to build, and then, it's fine, but patterns, this is where patterns come into play. So alternatively, let's clean this up a little bit. We can use a pattern which does exactly the same sort of thing here. In particular, let's take a look at, well, you know what? Let's go to the pattern library first. Why not? So if we go to the top here, of streams, patterns, events, and click on patterns. We can now just sort of browse by pattern category. So there are patterns that deal with randomness, like P Gauss, Gaussian distribution, P HP rand, P LP. There's hundreds and hundreds and hundreds of patterns. Let's see, what's another? Repetition. Yeah, all sorts of P gate, P end, P stutter. So a good sort of question is where to begin with patterns. So I'm going to show you one pattern first. It is P series. P series returns a stream that behaves like an arithmetic series, and you will probably remember array.series, where we provide a size, a start, and a step value, and this gives us in this case 8 values, starting with 0 with an arithmetic increment of 12. So P series is kind of similar. The difference being that it's not a method for an array, it's a pattern. And so we just do pseries.new. We actually often just omit .new because it's tedious to put .new before everything. Oh, Siri thinks I'm talking to her. She just picked up a whole lot of dictation stuff. I must have said something that sounded like HEYSIRI. Okay, so P series takes a starting value. Let's start at 0. We're just going to repeat, just do a recreation of this stream here. P series, we start at 0, we increment by 1, and we'll go forever. Okay, Siri, you gotta, I'm turning you off, Siri. Now is not a good time. All right, where were we? So let's say P equals P series, starting at 0, increment of 1, infinite. And this is just one flavor of pattern, right? There's tons of patterns, they all do different stuff. I'm going to focus on P series for now. And we're actually going to, we can't quite call next on, we can't just say next, right? Because it's just going to give us a P series. You can call next on anything. Next is defined for object, and unless an object is specifically a stream, it will just respond to next by returning itself. So in that sense, anything can be a stream. It's just that sometimes we want streams that are a little bit more special. They actually return a sequence of different values based on some algorithm. So we're going to say .asStream. And it actually gives us a routine, but routine is a subclass of stream, so it's kind of the same thing. This is what I was trying to get at when there's so many interrelated classes here. What's a stream, what's a routine, what's a pattern, what's an event, And to be honest, I don't think we really need to focus too much on the details here. I just want to try to get to the functionality of it all. So now we can just say p.next 0, 1, 2, 3, 4, 5, 6, 7, 8. There we go. So we have condensed this more, laborious construction of declaring a variable and manually incrementing it down to basically just 2 lines, really 1 line, and then just calling next on it. And of course, because this is a stream, we can say next n. For example, we'll get the next 4 values, So this is really convenient. And let's do a quick sound example, just to show you that before we even get into more complex stuff, patterns can be really useful for creating a sequence of sound data, of synths or something. So a quick synth-def, I think, is in order. Let's call this sine. And let's make an argument for frequency, argument for amplitude. Right, and env, let's just do env.kr, env.perk. Done action 2. Let's make some room. And sig equals sig times env times amp out 0 sig exclam 2. I think I did that right. So I think that's working, right? We have sound. I think I see level, so that's good. Let's bring it up a little bit. Okay, great. And just to check, excellent. So let's create a pattern for frequency values. So we'll say freaks equals p series. Actually, let's go with MIDI notes, right? MIDI notes p series. And I forgot one thing here. What if we don't make this an infinite series? Let's say just do 5. Right? We want 5 values. So 0, 1, 2, 3, 4. 5 values. What happens if we do next here? Nil. We get nil. Patterns, when they get to the end of their, whatever they're supposed to be doing, if it's finite and you ask for the next thing, it returns nil. But of course, you can always say p.reset and start back at the beginning. So we will start with let's start with MIDI note 60. We'll step by a whole step, so going up by 2 semitones, and we'll do 14 of these as stream. Okay, so we now have a stream of MIDI notes starting at 60, and it's going to go 60, 62, 64, etc. So now we can do we can do a simple routine. Or actually, maybe we can just do, no, we will do a routine. And we'll do 14.do, synth, sign, freak, and we do MIDI notes dot next dot MIDI CPS. Because remember, these are MIDI notes, but our synth expects cycles per second. And we'll just say 0.5.wait. And I know this may not seem particularly impressive. You could also just iterate over the array, 60, 62, dot, dot, what would this be? 88 or something? 14. I don't know. And passing this value. We've seen stuff like this before, but I hopefully by the end of this you'll see that patterns really do have quite a bit of flexibility to them. So that is this making sense so far? At least syntactically, general direction here, just to show that even just a basic pattern here can be used for a simple synthesis example. Guys are, yeah, okay. Guys are a little quiet tonight, but that's okay. I'm fine with that. Feels like kind of a quiet night to me too. All right, in Streams, Patterns, Events, a Practical Guide by H. James Harkins. The second category, Pattern Guide to Basic Vocabulary. This very conveniently gives us a very quick reference of some basic patterns, because a very reasonable question is, okay, P series, got it. What else is there? P what? P this, P that. They all start with a capital P. That's how they're delineated as patterns. So in quick reference here, P seek, P rand, P x rand, P shuff, P w rand, P series. There we go. We just saw P series. P geom, P white. And actually, I will vouch for this list. I think this is actually a really, really good summary of patterns that are used very, very commonly. I've used just about all of these. And so we'll quickly go through some of these patterns. So let's talk about pseek, arguably the most common pattern. Pseek accepts an array of values. and a number of repeats. And it will sequence through those values. So let's do next 1, 2, 3, 10, 1, 2, 3, 10, nil. Because we told it to sequence through this array twice. Of course, we could do inf here, and now we'll just get an infinite sequence of 1, 2, 3, 10, 1, 2, 3, 10, keeping in mind that we can also just do next n just to see, what we get. So 1, 2, 3, 10, 1, 2, 3, 10. That's pseq. Really handy if you just want to do something in a specific order and repeat that order a number of times. Prand is the equivalent of .choose. You've seen this before, right? We have an array, and we randomly pick an item from the array. That's exactly what prand does. So if we just say, next 12 values, here we go. We have picked randomly, and it's just a simple random choice each time, completely random, as random as computers can be. So 2, 4, 2, 6, 2. We got a single 8 in there. If we just keep running it, we'll get another random 12 values here. So this is really handy for just picking random value. If you want specific random values to be chosen, this is the one to use. Pxrand, I'm not even going to demonstrate this one. It's explainable. It is almost exactly like prand, the difference being that it will never choose the same value twice in a row. So, I will demonstrate it because it's fun. So what we'll see here, let's look at prand for a second. You can see we got 2 8s in a row. We got 2 2s in a row, 2 4s in a row at the end. Pxrand will never do that. As you can see, we got a 2, so the next thing is going to be a 4, a 6, or an 8. Then the next thing, it's a 4, so we get a 2, a 6, or an 8. So no repeated ones. This is really nice. I find this is really good for triggering samples. If you have like 10 different snare drum hits or something. In real life, when you play a snare drum twice in a row, you're never going to get exactly the same sound. It's always going to be slightly different based on where on the drum you hit it, how hard you hit it, etc. So Pxrand is really nice for triggering drum samples or something, because you're guaranteed you're never going to get the same sample twice in a row, which sounds really unnatural if you ever get the same sample twice in a row. It sort of gives away the illusion. You wouldn't really need, David, you wouldn't really need to get it to restart automatically, because you can just provide inf for the number of repeats. So, it's, when you run out of values, you can also, you can just, like if it's pseq or something, or pseq, here, we never really need to reset it. We can if we want, but it'll just keep going forever. And the other, well, let me get this other question real quick. So pseudo-random, roll a dice 6 times and expect it to roll through most. Yeah, that's basically, it's a simulation of a dice roll. Okay, let's go through a few more of these, and then I just want to show you more things you can do with patterns, because you're not just stuck with one of these patterns. You can combine them in very interesting ways. All right, so pshuff is like pseq and prand and pxrand. You give it an array, it then scrambles the array and uses that order and repeats that order, that random order, that many times. So let's do just something simple here. We'll do 1 through 5. Remember, this syntax here gives us an array, so we can this is totally legal here. And we'll do pshuff. So pshuff, and let's get the next 15 values. And as you can see, pshuff has scrambled the order, and we've told it to repeat forever, and we've grabbed the next 15, so we get that same order of 5 values, 5 values, 5 values. Yeah, Dungrel is sort of right. You can have it in a routine, and I think that's one way to do it. You can just you say next, and then you can do a conditional if nil, reset the pattern, and then run next again, and you'll get the first value again. So it is possible to do that. I've never really found any reason to do that, just I think based on the context in which patterns are usually used. That's pshuff. pwrand, I use this one quite a lot. The W stands for weight, like W-E-I-G-H-T. So pwrand. Now, this one's a little bit different. You get an array of values. Then you provide an array of weights. And these weights have to sum to 1. So let's say 0.1, 0.8, 0.1. And we'll repeat forever. Now, this means 80% of the time, this pattern will choose 2. And 10% of the time, it'll choose 1. And the other 10% of the time, it'll choose 3. So if we grab the next 20 values, we see approximately 80% 2s, and then the other 20% is either 3 or 1. So this is a way to make random choices with specific weights. Now, if you have a lot of values here, it can be actually quite annoying to make sure this array sums to 1. So here's a neat trick. Let's say we just want a lot of 1s. Let's just say, I don't know, 50. And then 10, and just provide sort of weights that feel intuitive, right? Now, these don't add to 1, but you can say dot normalize sum. Let's spread this out a little bit. And dot normalize sum is a method for arrays that will preserve the relationships between them, but scale them so that their sum equals 1. So now we have the same percentages, basically. This is not 50% of the time, 10% of the time. That's not how it works. These are just relationships. And then if we use normalized sum, we get this array, which actually does sum to 1. So now, if we run this, we should get a ridiculous amount of 1s, some 2s, and almost no 3, 4s, and 5s. Yeah, so that looks about right. We get mostly 1s, a sprinkling of 2s, and we got 1 5, which is actually the rarest thing we're going to get. So that's pwrand. All right. Onward. We've seen pseries. pgeom is, if pseries is like array.series, then pgeom is like array.geom, where instead of an additive increment, we give it a multiplicative increment. So let's start at 1, and we'll grow by 2. And we'll do inf, and then let's grab the next 6 values. Oh, I forgot as stream. Right? If it's not a stream, and patterns are not streams, they're related, but they are not the same thing. If we don't convert it to a stream, then next and next n are not going to work correctly. So this is a geometric series, 1, 2, 4, 8, 16, 32. This is often very nice for manipulating frequencies and amplitudes, which are sort of on an exponential scale. You do want to be careful, though, because you can't immediately tell where this is going to end, right? Let's say if we do like 1, and we'll do 1 point. Let's start at like 0.01, and we'll multiply by 1.5, and we'd like to stay below 1. If we grab these, that's all fine. Keep going, and there we go. We got 12 values in, and then now we're over 1. So I guess now is a good time as any to talk that to make sure everyone knows that patterns respond to a lot of the same methods that numbers respond to. So we can have this pattern here, and then we can say dot clip. I think this will work, 0 and 1. Yeah, and it returns, a pn array op. This is a sort of an internal class. This pattern received this method, and in response transformed into a different type of pattern. And we, of course, also have to do as stream. And you can just sort of ignore these crazy words here. But now, I think if we just do, next 15, we have successfully clipped our values. So we are doing a geometric series in as much as we can, but then the results of this pattern are filtered through this clip method. So they're going to be constrained between 0 and 1. You can also do stuff like, any method that a number can receive, like square root. So now we have the square root. Here's the number, and the square root of 0.01 is 0.1. So any sort of math is legal here, and you can also add, subtract, and divide patterns just like their numbers. And then we can just, on a new line, p equals p dot as stream. So there we have a pgeom plus a p series as a stream. And here we go. You can see we have our geometric series, but we add 1 to this item, add 2, add 3, add 4, etc. So adding and subtracting patterns is totally legitimate, and giving them methods. And you can also nest patterns. This is, I think, where the strength of patterns really comes into play here, is that, okay, so if a pattern, like let's say we have pseek. And we're going to do 40, 50, 60, forever, right? As stream. Right? No funny business here, 40, 50, 60. So what happens, think about this for a second, if instead of, after 60, we have another pseek. This one goes 1, 2, 3, twice. Okay, and it starts to, at least to me, it starts to look a little confusing here, because we've got just so many various parentheticals. So sometimes, I'll opt to do something like this. However you are able to sleep at night with syntax. Whatever feels readable to you is probably the right thing to do, although it never hurts to take advantage of a little bit of white space. Is it possible to weight the most prominent partials of a spectrum of a sound file and use patterns to add some sort of synthesis to transform the spectrum? Yes, it is. It's not the most trivial thing in the world. Yeah, we'll do something like that. It will, even with this very simple synth-def that we made, which is just a single sine wave, we can use patterns to generate harmonics of a fundamental and use PWRAN to focus on specific partials, and we can create this sort of additive synthesis spectrum. So we'll make sure we do that. That's a really fun example. I do something similar to that in tutorial 10, so I would definitely echo that recommendation that you go and watch that, because there's some good synthesis examples in that one. So what happens here? We have pseek as a stream, and it's going to sequence through its array forever, an infinite number of times. And the first thing we get is 40, and then 50, and then 60. And then what? Does it output a pseek? Well, no, it doesn't. It when a pattern encounters a pattern in its course of operation, it embeds the result of that nested pattern in its output stream. So here we'll get 40, 50, 60, 1, 2, 3, 1, 2, 3, 40, 50, 60, 1, 2, 3, 1, 2, 3. And let's confirm. Let's just grab 30 values or so. So there we go, 40, 50, 60, 1, 2, 3, 1, 2, 3, etc. And if we were, being sort of careless here, I don't know if careless is the right word, but if we made this nested pattern infinite, then pseek, even though it's supposed to repeat its outer pattern forever, it'll never be able to repeat even once, because it gets stuck on this internal infinite pattern. As you can see, we get 40, 50, 60, and then it gets stuck on this infinite pattern. We could even put another pattern, here or something. But we're not going to do that. That's crazy. Anyway, so the idea of nesting is really, really convenient. Another example is, let's say we have, let's go back to pgeom, and we start at 1. We'll multiply by 1.1, 1.2. Why not? And we'll do 10 values. And if we want to repeat this geometric series forever, what can we do? We run out of, we're only doing this 10 times, and once we hit our 10th value, we just start returning nil, because we're saying, give me the next value, give me the next value, and the pjump says, whoa, I'm done. Like, I got nothing else for you. So so knowing what we know about nested patterns, what's the solution here? If we want to repeat this sequence of 10 values again and again and again, how can we do that? So I'm asking all of you, what would you do to, we want these 10 values over and over again. But there's no, we can't say inf. That doesn't work, because, it's just going to keep doing its geometric series thing. We want to repeat these first 10 values. Any ideas? Assign it to an array and then have a p-series using that array. P-series isn't really going to quite solve it, because p-series is a lot like, pn. Pn's a good one. That would do it. Again, putting it in a routine with a loop, well, I think that would be a little bit, it's not the most elegant way to do it, because we're going to need, the routine is going to, we're going to need to somehow reset the stream, right? But, so we could do Pn. Pn is one way we can do it. Pn is a pattern that repeatedly embeds a pattern. Alternatively, we can actually do this using pseek, which we just covered. So let's all we have to do is say pseek and give it an array, and in that array is just one pattern, right? This pgeom, and we want to repeat this an infinite number of times. All right, so let's take a step back. We had this pgeom that produced 10 values. We want to repeat those. And we can't do it using just pgeom, so we can take advantage of pattern nesting, put it inside a sequential pattern, so pseek or pn would work, and then repeat that pseek an infinite number of times. So now we have 1 through 5 point whatever, and then pseek kicks in, it gets to the end of its array, right? Because it embeds the pgeom, and it says, oh, infinite number of repeats. So let's do it again. So it does it again and does it again. Oh yeah, I had a feeling, unfearing, that you meant pseek, but you said p-series by accident. So yes, you are correct. Yeah, you had the right idea. And just to show you, I believe Pn will also work, but you provide the pattern first and there's no array, right? I think this works as well, and it does. Yeah, so you don't have to do the square brackets, so it's a little bit easier, I guess. So Pn, you provide a pattern and the number of times to embed that pattern. Basically the same idea. Okay. Just a few more patterns, I guess. Just there's a couple more that are worth mentioning. P-white, this is the same as R-rand. We know R-rand, it's linear distribution. P-white is exactly the same in many ways. We do a low and a high and a number of repeats. And as you can see, we just get a nice random sequence of values. And just like when R-rand, if one of those is a float, we get floats. The same is true of P-white. Right? So now we get 30 random values in an array. P-exbrand is just like exbrand. We're always going to get floats, even if these are integers. So we get an exponential distribution. And of course, we can round these, so now they'll be integers, even though it's still an exponential distribution. So just reinforcing the idea that patterns understand and respond appropriately to math operations. And coding boot camp instead of a college degree in computer science. Oh, I don't know. I mean, why not both? So here's one more interesting thing about patterns here. P series. So we can also use iteration methods like collect, select, reject on patterns, and those can make sense of those as well. So if we collect over the array, remember how collect works on, if we collect over the pattern, excuse me, the way collect works on arrays is, it returns a new array based on what its function returns. So here we just return, so we can do n times 2 minus 1 dot as stream. And here we get the results. So instead of 0, 1, 2, 3, 4, 5, etc., we get that value times 2 minus 1 as an example here. And a new method here, select. Select is like collect, except instead of returning a new array based on what the function returns, it will preserve the items in the array for which this function returns true. So for example, if it's odd, it is preserved in the output. Right here, if it's even, it's preserved. So it basically selects items from this array and keeps them in the array if this is true. We can also do n dot is prime. Oops. Forgot to select everything here. So 2 and 3 are prime. And patterns do the same thing. So now if we just, and this, this is an infinite series. And so if we say, give me the next 20 values, it's going to start with 0 and say, no, that's not prime. It's going to go to 1 and say, that's not prime. 2, that's prime. Oh, I forgot to as stream. Right. So there we go. So we can get ourselves a list of the first 20 primes. We can get as many primes as we want, really. All right. So do take a look at these patterns. I've covered, really like over 50% of my pattern usage. I do not really dip into the complex, crazy patterns. I can usually get by just fine with pseek, prand, pxrand, pwrand, pwhite, and pxrand, also very helpful. Okay. And we've seen a simple sort of synthesis example. Now let's do another one real quick here. So let's think about what we want from a synthesis perspective. We've got our synthDef. I think I might actually copy it and paste it down here just to give ourselves some more white space to work with here. And let's say for frequencies, I think the biggest challenge of patterns is translating your own musical thoughts into the appropriate patterns or combination of patterns. So let's say we want to choose from, and feel free to throw out suggestions here. We'll just pick notes from a major scale here. So we can do, we want to pick randomly from notes, and I guess we can do pxrand here. So pxrand takes an array, and a C major scale would be 65, 67, 9, 71, and then 72 if we want the upper octave. And we can also do this with scale.major.degrees plus 60. That gives us C through B. If you want a convenient way to make scales, you can just use scale dot whatever type of scale you want and then convert that to scale degrees and transpose as necessary. And let's say amplitudes. Let's do P exparand. So we're going to do a nice sort of even. These will be fairly quiet, but occasionally getting up to maybe 0.5. And for, let's see, we're going to have some wait times, right? I know I keep saying wait, like W-E-I-G-H-T or W-A-I-T-S. Let's call this durations, durs. And we'll do pwrand for this. So, and of course we need 2 arrays. So we might wait for 1/10 of a second, or we might occasionally wait for 2 seconds. But we will favor the short wait times. Right? So this pattern will choose 0.1 90% of the time and 2 0.1% of the time. And now we will create a routine with a loop, and we'll say synth.new sign with the freak is equal to freaks.next.midi CPS. You know, maybe I should call this notes or something to be consistent here. So we're going to get the next value from the notes stream converted to MIDI CPS. Amp, we can leave these values as is, amps.next. We don't need to do any sort of conversion. So, and this is an infinite stream. It's just going to pick with an exponential distribution between 0.01 and 0.5. And then we are going to doors.next.wait. I see what I did. Message wait not understood. Receiver a pwrand. Can you guys see what I did wrong? We get 1 note, and then the wait message is not understood because when we call next on durs, we get a pwrand instead of a number. So I forgot to as stream. Ah. So we're getting these notes from C major scale, and we get these bursts of quick notes because we're most of the time having a nice short wait time. But every now and then we get a 2-second break because we get a note and then we wait for 2 seconds. And and actually, interestingly, we can modify this on the fly a little bit, I think. If we, let's make this consistently a lot louder. Yeah. I'm redefining amps, but this routine is just playing. And every time it loops, it checks amps and says, give me the next value. So at any point in time, I could change this pattern. I could even replace it with an entirely different pattern. And, you know, it just says, okay, amps is now this thing. And it says, give me the next thing. Whatever you are, give me next, right? We could even set this to be, you know, 0.5. And now we are at a constant 0.05. Because remember, any value, any object is perfectly fine responding to the next message. You know, most things, when they get the message next, they just return themselves. You know, oh, me.next, okay, here I am. But streams are a little bit different. When you say to a stream, give me the next thing, it goes to its algorithm and says, okay, here's the next one. Okay, now I've got this one for you. You know, like pseek and pseries and all those things. do a little bit faster here. And maybe we'll make it 95% of the time, these short ones. Oh, I started a second routine. I didn't mean to do that. Now let's separate these clumps out. So there's those. So 1% of the time we get our 2-second wait. Because SuperCollider doesn't care about that, weirdly. Yeah, it's okay with commas after the last thing in an array, I think, right? If I do, okay, you shoosh. There we go. So I can hear myself think. I think it doesn't care about that. Like if we do this, yeah, it just doesn't care. The error in your problem set is because I think you did this. You put a semicolon after an item in an array. That's like, you know, doing this. And what? Wait, what? Is it? Okay, I don't quite understand that, but it screws stuff up. A semicolon tells SuperCollider you are at the end of a statement. So I don't understand why that works. Okay, bizarre stuff is happening. But I remember, if you're talking about the problem set that I think you're talking about, it's because you had a new synth with, you know, symbol value pairs for the arguments, but you ended one of them early with a semicolon. So it's fine to have no comma here, or a comma. I think it's also fine to have a semicolon. But if you put a semicolon here, weird stuff happens. You know, I don't know. Okay, so that's a simple sort of synthesis example with streams and being able to define algorithmic sequences of values. And you could vary with minimal effort, just add a few more arguments to the synth-def. Maybe instead of a sine wave, a sawtooth wave, and then you can run it through a low-pass filter, and then, you know, add an argument for the cutoff frequency and put that here, and whatever. You can have a synth-def that plays sound files, and you can have an argument for start position. You know, if we have time at the end, we'll get to it. But I want to take our understanding of patterns to the next level. And in fact, tutorial 10 just kind of drops right into it. And here I'm talking here about a class, everyone's favorite class, called Pbind. So Pbind, I think we need a little bit of a backstory for Pbind. It says combine several value patterns to one event stream by binding keys to values. So first of all, what's an event stream? Second of all, what's an event? So these patterns we've been dealing with here, pxrand, pxprand, pwrand, these are what we call value patterns because they return values. But patterns don't always have to return values. Pbind in particular returns a stream. When you play a Pbind, it returns a stream of events. So an event is, and this is where we get into very vague terminology, just because necessarily all these ideas are very, very abstracted. They're generalized in such a way that we have these, you know, it's what is an event? Well, it's an environment that represents an action. You know, what is a computer programming language? You know, it's tough stuff to really define. Fortunately, I know this always feels like a weird thing to say as an educator, but I wouldn't worry about it too much because it's not something that I often have to think about or ever really had to think about. But I'll try to give you a bare bones foundation of event and what Pbind does in sequencing events. So there is something called the default event, and events are delineated with parentheses, and we can play the default event and we get a sound. And we can store this as the letter E. And now we can say, okay, E, what are you? Well, I'm an event. And if we just evaluate E, we can see that it is a delineation of parentheses, and it has a bunch of symbol value pairs. You know, what instrument are you using? Well, I'm using the default instrument. Instrument is a key that represents what synth-def we are using. So in fact, there is a default synth-def called default. Actually, we can. So if you're at home, you can boot the server and run this line, and you should hear a sound, even though you didn't actually make a synth-def called default, but it is there, and it exists, and it's useful because a lot of the example files use the default synth-def. The default event also has some other parameters, like amplitude, which has a default value of 0.1, a sustain value of 0.08, which is an attribute which tells the program how long to wait before setting the gate back to 0 and effectively ending the envelope. You can override the default synth. You absolutely can. And for that reason, there's a method called make default synth-def. And it's a class method which basically recreates, it overrides your override. So it basically recreates the default synth-def, so your help files will work again. I think that's why. Yeah, this method is called in order to build the default synth-def, which is stored under the key default. Okay, so this is an event. We can even play the default event just by providing, this is really crazy, just two parentheses with nothing in them, dot play. This kind of blew my mind the first time that makes a sound. Like, we provided literally no information, and it says, oh yeah, I got you covered. There's a note. And so the some of these keys like amp and freak, right? Freak is middle C. This is the frequency of middle C. We can specify, freak 800. We can say freak 800 and sustain 2. And it now sustains for about 2 seconds, right? So the gate is on, 2 seconds later, the gate is off. We can set the amp to be, let's shorten the duration again, the amp to be 0.5 instead of 0.1. So these are events. More specifically, we are playing a version of the default event. And events have different types. And the default event type is something, I think this will work. Yeah, is called the note event. So let's go, I think let's go into the help file for Pbind. And if we search for event, there's a paragraph down here, synth-def and event. Right, the keys used in a Pbind, is somewhere where it says, okay, this is what I was looking for here. By default, events play synths on a server. That's exactly what's happening here. We play an event, and by default, it creates an event. Creates a synth on the server. And this default event type is called note events. And they have a variety of keys, and we're using some of them here: freak, sustain, amp. So let's just keep this in mind, and let's modify our synth-def. I'm going to change this to be a gated envelope. So instead of a percussive envelope, it's now going to be an attack, sustain, release envelope with an attack time of 0.01, a sustain level of 1, and a release time of 0.01. So basically, it just quickly goes up to full sustain, and then we give it a gate argument. And we can set it to 1. It'll sustain indefinitely. And we can give it a gate value of 0, and it goes away. Okay, so here is our new synth-def. I guess I should probably, no, it's fine. I'll just overwrite it. So now let's go back to our event here. So here, now what I'm going to do is add another key. I'm going to add the instrument key. Doesn't matter what order. So now we have overridden not just synthesis parameter keys, but also the key that tells the event what synth-def to use when generating a note event. So it's now using the synth-def called sign. And so it's, this has its own set of arguments, gate, and sustain assumes that the synth-def has a gate, and it will send a gate value of 0 this many seconds later. So we can just sustain it for 1 second. 0.5. I don't know if that's high enough for everyone to hear. Okay, so this is event, and this is kind of as much as I want to talk about it, just to show you that there is such a thing as an event, and its syntax looks sort of like this. I rarely use event explicitly, but Pbind is really, really useful. Did I delete? I wrote Pbind. Yeah. Okay. So Pbind basically is a pattern which, unlike pseries, pgeom, pran, or white, pexparent, instead of spitting out values, it spits out events. And by default, the events are note events, and so they create synths on a server. And so in Pbind, we provide a series of symbol value pairs. Let's just get right into it. So we're going to make a Pbind, and we need pairs. And the first thing that I'm going to do, it's not strictly necessary, is specify the type of event. And we are going to do note type events. Then, if we're going to be making note type events, we need to know what synth-def we're going to use. So we are going to use sign. Oh, sorry, that's not right. Instrument, right? Sign. So these are the keys or the symbols in the event, right? This tells the event prototype what to do. So event prototype says, oh, okay, note type events, got it. So I'm going to need to know what synth-def to use because note type events generate a synth on the server. So it's going to use the synth-def called sign. And once we provide the name of the instrument, or the name of the synth-def, if you want to be more specific, that determines the remaining keys that we can use. So freak, we'll just start with 440. Let's do 800, different frequency. Amp, we'll keep it at 0.2. And we don't want to say gate, because if we say gate 1, then there's no real way to give that a value of 0. So we'll do sustain, right? This is all built into the event architecture. And so this is a value provided for how long between the gate is 1 and the gate is 0. So we will say just 0.2 seconds. And we will play this Pbind and give it a name. We'll call it P. He's flatlining. Nurse, scalpel. We lost him. Yeah. Okay, so that's not very exciting, but you'll notice that we heard 1 synth per second. That's because when we play a Pbind, there's an additional parameter, dur, which is the amount of time to wait before scheduling the next event. So by default, that is 1, and this is it sounds and looks like a value in seconds, but it's technically a value in beats, because Pbinds, when we play them, they play on a particular clock, and by default they use the default tempo clock, which has a tempo of 60 beats per minute, which is convenient because at 60 beats per minute, durations in seconds are equal to durations in beats. 1 second is 1 beat. So we could also change this to 0.5, 0.25, We can make the sustain a lot shorter. Bring the amplitude up. Right. So the arg amp, does that control the synth sign, or is that from the event? Well, that's a really good question. If we happen to use a synth-def that includes an argument called amp, then this key amp is being used for that argument. So if we called this like something else like volume and volume, now if we do this, this has no effect. Right? This value for amp is getting placed into the default, into the event, right? So if we were to sort of look at the event, you'd see, you know, instrument, freak, whatever, and you would see amp, and you would see a value of 0. But this is creating note type events with the synth-def called sign, and sign has no amp argument, so it doesn't. We can put 1,000,000 for amp, and it's just not going to do anything because this particular synth-def does not have an argument control named amp. So in this case, you know, we'd need to change this to volume, and now of course we get nothing because volume is 0. So we bring this up and bring it up again. Okay, and I also want to point out that the order here does not matter. You can put these in any order you like, because when you play a Pbind, each event that it generates, it goes through all of its parameters and says, okay, I'm going to bind note to the type key. I'm going to bind sign to the instrument we're using. The dur key, I'm going to bind 0.25. Don't get why the amp argument in the event still creates sound. Do you mean here? Let's change this. So it still creates sound because the default event type is note events. So we're going to be making a synth on the server. Without this, we'd be using the default synth-def. But we are not using the default synth-def. We are using the synth-def that I created called sign. And so it makes a synth, and it is providing, we have a key called frequency, which is 300, and that happens to exist here, so that gets plugged right in. So this becomes 300 instead of 440. And sustain, it has meaning to the event, to note type events, and it assumes that the synth-def has a gate argument. And you know, amp, this is going to be present in the event, but it's not going to have an effect on the synth-def because amp does not exist in this synth-def. So again, we can just set this to 0, and we still get sound because the parameter that actually controls the amplitude is called volume. So we can keep amp in there just fine, but this is what we actually need to do to change the amplitude, is adjust a parameter called volume. Yeah, if we, so in the Pbind here, let's go back to our original example here, amp, and now we'll say amp. Whoops. So that's all working just fine. Just so now if we said, you know, volume 0, this isn't doing anything, right? No effect whatsoever, because, you know, Pbind is perfectly happy placing a random key in the event. You know, we can say blurf 1,000,000. Is that 1,000,000? That's 100,000. 1,000,000. You know, you can put as many random keys in there as you want, but if we're making note events, then it's going to assume these keys exist in the synth-def. And if they don't, it says, yeah, that's not my problem. I mean, you want blurf to be 1,000,000. I'll make blurf 1,000,000, but there's no blurf here, so nothing's going to happen. So if we change, you know, this to like something else, then now we need to set something else to be that value. So Yeah, this is really not easy stuff to explain or understand. I'll give everyone that. I mean, I think I hope it's the case that, you know, once you get the hang of Pbind and sequencing data, things will start to make more sense. I hope people have a lot of questions because it's just such a wide and generalized idea, you know, patterns. So hopefully there'll be a lot of questions in class and on the stream and stuff like that. But let's go back to what we had, and let's just have some real talk here for a second. This is a really dumb example because we're not using any patterns. We're just using Pbind. You know, this is the equivalent of doing, you know, this. Just, you know, using a pseq with one thing in it and just repeating it forever. But we don't have to do that. Right? Let's keep this at 0.25 for now, but let's do the frequency here. Oh yeah, there's a lot of code here. Yeah, but sort of. Yeah. Yeah, Dongrul, you can think of Pbind. Pbind is the technical definition of Pbind. Pbind is a pattern which generates a stream of events in response to the play message. So not necessarily synths, but because the default event type is a note event, which a note event generates a synth, you can think of playing a Pbind as producing a sequence of synths. And the note event is defined in such a way that when you provide the name of the synth-def, you then have access, or you know, the remaining keys you provide, it's expected that you will be providing values for the arguments. So let's do pseq, and we will provide the array 100, 200, ... 800, and we will repeat that forever. I want to make this percussive again, so we'll do perc 0.3, and we'll get rid of this gate argument. So now we don't need sustain. We can keep sustain. Yeah, why is that so quiet? Awfully quiet. Oh, yeah, because this third argument is level. I meant to get rid of that. I don't want the level to be 0.01. Let's make another argument for release time. Right. Now we can say release 0.1. We can get a little fancier here maybe, and say pseq. And inside the pseq, we'll have a pseries. No, pgeom. We'll start at 100. We'll grow by 1.2. And we'll have this be 12 items long. And just to be safe, we'll clip it between 100 and 10,000. And, you know, let's add another pattern here. So we can say the release will be pseq, and we'll do a pseries. Starting at 0.02, and we'll increment by 0.02, and we'll do that 12 times. So now the release of the envelope over the course of 12 note events is going to go from 0.02 to 0.04, 0.06, 0.08, etc. So, and then the process will repeat over again. So these will remain in sync, right? The geometric frequency pattern and the release. A sequence of random clusters, yes. Yeah, let's do that. So, all right, let's shift these patterns around. Let's do a long release. Let's do pexp rand, somewhere between 4 and 6 seconds. And we'll turn the amplitude down a little bit. And I think the way to do this, there's a pattern called, yeah, let's do pfunc. I think this will work. So pfunc returns a stream that returns, or is it? I think pfunc n, is that in, I actually just learned about pfunc n. I think it's like, where's the practical guide? Yeah, you provide a function and a number of repeats. Gets values from the function, but stop after repeats items. No, you've got to boot the server, first of all. And once you boot the server, then you can create a synth-def like the one you see here. So you just want to run s.boot first to make sure you have green numbers in the corner, and then it should work. So I think with pfunc n, we're going to provide a function. And we'll just say, we'll make a array.fill. Let's say 5 exprand 150 to 3000. So this gives us an array of 5 values for our frequency pattern. And we'll just say inf. Is this going to work? Oh, we want the duration to be much. Yeah, if these are long releases and they're happening 10 times a second, let's try like 3. So there is a sequence of random clusters. Let's turn the amplitude way down and do like 30 of these. Now, so every 3 seconds, we get a new note event using the sign synth-def. And the frequency is a pattern that returns each time it's called an array of 30 random numbers. And we can do pexprand here. Let's say somewhere between 0.2 and 4 seconds inf. Ooh. So this is more or less how I work in SuperCollider. I will make an instrument with a bunch of parameters, and then I'll make a pattern and try to find an interesting way to create a sequence of those synths. So let's add another argument here. Pan. And we'll set it to 0. We're not going to exclaim 2 on this, and instead we will say sig equals. Oh, good question. Good question. Let's back up a second. Good question, Dunkrul. So Why did I wrap with a pfunc? It's because the quick answer here is when you are working in a pbind, you need to think in terms of patterns. So if I just did this, if this is what you're suggesting, just provide an array, right? What's going to happen here is that when we play this pbind, this gets evaluated once, and then this array of 30 values is what is embedded in each event generated by Pbind. So right, because what's happening in the background here is that some process is calling next on every item here. It's calling next on note, next on sign. It says, of course, these things are just symbols. So when you say next on a symbol or a number or anything, it just returns the same thing. And that's actually what we want in this case. We want to keep using this synthef. This could be subject to patterns if we want. We could pick from like 3 different synthefs. But here, we don't want the duration to be the same every time. So we provide a pattern, which is then, internally converted to a stream and then called next on. So we'll get a new, random value with an exponential distribution between 0.2 and 4. And then the next event calls next again, and we get another event and another. And this will happen forever, inf. But here we've essentially provided an array. And when you call next on an array, it just returns itself. And so that's no good. If we want different frequencies, we want to use a pattern. And in this case, pfunc n makes some sense. We want to close that function, comma, an infinite number. So now we have a pattern that returns a random array of 30 values. And when this is converted to a stream and we generate events, then the pattern's going to say, okay, here my next item is this new array. It's going to call this again and again and again, and we're going to get a new array every time. So in that sense, it's necessary to wrap that in a pfunc n. Right, if we did dur random between 0.2 and 0.8, I screwed something up here. What is the problem? 738. Is that comma screwing us up? Yeah. Notice that we've got the same delta time. Oh yeah. P.stop should stop it. But if you run this twice, like run it once, run it twice, then P.stop is not going to help you. It's the same problem. I've been hitting command period nonstop here. It's like if you have a synth, x equals synth.new, and it makes a sound, and then you do x equals synth.new again. Well, you've just overwritten your global variable with a new synth, and the old one is no longer accessible. Same deal with patterns. There are ways around this and stuff, but for now, when you say something equals pbind.play, you want to keep track of it. And if we run this twice, then p refers to a different pbind. But command period is the way to do it. So yeah, so just to again for Dungrul's question, here this is basically a fixed value, right? It's the same sort of problem we have when we do rrand, 0.2 comma 0.8 exclam 8, and we're like, okay, 8 random values. Ah, wah wah, right? So this is duplicating the random value here, and it's a similar thing that's going on here. This is, this is ultimately a value, and when pbind.play creates a process that calls next on this thing, we just get the same value every time, which is why we need to think in terms of patterns. So here we get different dur times, different periods of time between events. And remember, patterns respond to math. So we can say round to the nearest multiple of 100. We can also do this here, of course. I think. Yeah. Yeah, so we can have the contents of the function itself round to the nearest value of 100. Or we can do it here. But this sounds really kind of dry and boring to me. So think back to our conversation about how you can add two patterns together. Like patterns can be, you can perform mathematical operations on patterns, and you can also combine them mathematically. So how could we detune all of these frequencies slightly? What could we do with the pattern provided for the freq key in order to detune all of them just a little bit? Any ideas? Well, we've got these values. Add a random offset with the X brand. Yeah, that's a good one. We can use X brand. So we can like add P X brand somewhere between, I don't know, 0.1 and 3. Just inf. Right. Yeah, P white would be good too, I think. Yeah, so let's just try this first. That's not quite enough. Let's do... Yeah, so Px brand is going to favor values towards the low end. So I think better might be to multiply by P white somewhere between -1.0 and +1.0, and then say MIDI ratio. This should sort of ring a bell with what you guys were doing with some of the earlier assignments, because this is going to pick a random value between -1 and 1 and treat that as a value in semitones and convert it to the appropriate ratio, and then multiply it by our Pfunc n. So, and yeah. Oh, but it's applying this to all 5 values. So I think what we want to do here is let's do another Pfunc n. Let's I never really quite know how to make this look readable. Maybe we'll put the multiplication sign on its own line. So we want to say array.fill 5 rrand -1, comma 1, making sure one of them is a float, and we need this to be in curly braces. Oh, we need 30, right? We have 30. I was thinking of the older version. So we have 30 of these, 30 of these, dot MIDI ratio. And do this in infinite. Oops, we need that, that, and that. Pfunc. I think this should work. The durations are all kind of similar. I'm going to spread it out. And I don't want to, I think we're detuning it too much. It goes up a semitone and down a semitone, so. All right, so I was going to add a pan argument. We had it up here, and so let's go ahead and do that now by letting pan2 control our pan position. So now, if you're on headphones, I think you should be in for a treat here. So we've added a new argument called pan, and for pan, let's say we just want to take each of these and oh, and I want to simplify this a little bit. I think the chords are nice, but I feel like the Pfunc n is sort of obscuring the essentials here. So, all right, so now I think we should just have a single note now. So we're just picking a random value. We'll make this shorter. So we have a random value here. Turn this down a little bit. Dot round times an offset, comma. The problem is, I didn't put anything for pan. Pan is nothing, so it says pbind should have an even number of args. So now we'll do pwhite between -1.0 and +1.0. There we go. Whoa. That turned out better than I thought. This could be our outro music. Okay, what I want to be able to do is to change the pattern without having to stop it. And okay, trying to think of there are multiple ways to do this. Patterns have, this is really the most vanilla version of Pbind, but there are all sorts of interesting things you can do to modify this. Okay, so first let's go into the event help file. And for note events, there actually is this very, very attractive hierarchy of keys for dealing with the frequency of a synth-def. And I want to, in tutorial 10, I talk about this and that, basically what the bottom line is, you should name your frequency argument FREQ because it gives you access to this hierarchy of ways of specifying pitch. Right? So we're specifying freq, but we could specify any of these other combinations of keys, like for example, MIDI note. Even though MIDI note is not defined in our synth-def, we can still provide it as a key, and it will automatically get translated into this value. So let's clean this up a little, make it a little bit more boring, but we will get excited about this. This is gonna be good. So we can say, if we say frequency 500, let's just do 200 here. I'm so indecisive. Let's just do 500. Okay. So now, and we'll do 0.2 and a short release. And yeah, so we still have our panning, right? But we're just making a single frequency, 500. Now, if we say MIDI note, and we'll just do middle C, 60. Right, so MIDI note works just fine. And this is really handy because you can go into, this is in the event help file. And at the bottom, it talks about events and patterns and various keys that you can use. And I think this hierarchy is also in the Pbind help file. Right. So we have, freq plus detune, and then one level behind that, MIDI note, C transpose plus harmonic. So what I want to do here is do MIDI note and harmonic. So we have MIDI note and harmonic. So let's do MIDI. What was that value? We had a value of, I guess it was like 100. That's approximately MIDI note number 43. And so then we're going to say harmonic. This is the harmonic number where 1 is the fundamental. And we'll do P exp rand 1 50 inf.round, round to the nearest integer. And so we'll do pxbrand here again for some more randomness. And the release time, we'll do pxbrand 4.6 like we had before, somewhere between 4 and 6. We'll turn the amplitude way down because now all of a sudden we're going to have a whole bunch of synths with long release times, and so we want to turn the amplitude down accordingly. Right. And I believe we can use the detune key as well. So we'll detune these all by some value in, I think it's hertz. Come on. There we go. Try between 10 and 10. That's cool. It's a little bit more than I was expecting. Let's try between 4 hertz. Let's make this 30. Okay. This is sort of like what we just had. All right, I see some questions, so I'm going to answer some questions here. Oh, gosh. So, yes, I've done some granular synthesis. I have a tool. It's like a little GUI interface called Granulator EF, which is on my website, which you can download. This is totally not related, but it looks like this. And you can load a sound file, and then you can do various granular synthesis stuff in it. Maybe we'll get to this later in the semester. And I just quit the server because that's what it does when you close the granulator. But we're back. Okay. Can you have like all the odd frequencies on the left and all the even? Yes. That's good. I think I know how to do that. There's a pattern called Pdef. So basically, I mean, there's a pattern version of everything. I know that the instinct is to do like if, then, whatever, like sort of vanilla if, but you have to think in terms of patterns when you're inside of a Pbind. So, and there's also a pattern P-key, which basically allows you to access a previous key. We'll try that. I don't know if I don't know. I usually have to honk around with patterns before I can, if someone suggests some new thing, but maybe we'll try that. So yeah, conditionals is the right way, but you have to use the pattern conditional otherwise, because if is just a value and it's not going to behave like a pattern. Where would we check all the listed parameters in the event? That's a great question. I was looking for that all last night, but the you don't really need to know because most of the time, you're either overriding them with the arguments in your synth-def, or actually, okay, there is sort of a place where you can look. If you go back to, where's my help? There's my help. Here it is. If you go to a practical guide and you go to event types and parameters, pattern guide 08. So yeah, so Dongrul, you can go here. A common question is, which parameters have special meanings in Pbind, which is essentially your question. Where could we check all the list of parameters in event? And perhaps surprisingly, none of them do. And I would suggest you read this. As is always the case, the help files are a little bit, complex in terms of language. But if we go down, we can see that, these are parameters which are common to all events. Delta, which is calculated from dur and stretch. So, we have this dur pattern we're using. Add action, amp, instrument, group. So these are, there's a note type event. And then I think there's also there's a help file called event types. And this tells you the various types of, so there's note type event. I don't think this tells you the keys for the default event. I don't know. I was struggling to find a very transparent and clear help file that just laid everything out. But event is a really sort of, I don't know, I find it to be a little bit obscure in nailing down an explanation and a concrete way of looking at it. But yeah. So we have like 8 channels. Can you have like frequency 1 to 50 designated to? Yeah, you can do all this. Most definitely. Is there a Markov chain? Like a Markov chain pattern? Not that I know of, but I would not be surprised if one exists. Let me let's try something here. Let's do pan. We're going to do a pif condition. I need to see an example of how this is used. So I think we just provide a pattern for the condition. This is, and again, we can't just say point3.coin. That technically does return true or false, but not in pattern town. Point3.coin is going to return true or false, but I think true 30% of the time. So it's inside of a pfunc. So we want to say if p key at harmonic dot let's try something that's very easy to hear. So if it's greater than 15, so I'm going to try to put all the low harmonics in the left. Let's do greater than 10. Greater than 10. Then we will do -1, otherwise +1. I don't know if this is going to work. Basically, we're doing a pattern for if, and we get a condition, which is a pattern. This is a p binary operator. So it's going to check the harmonic key, and this is going to be somewhere between 1 and 30. If it's greater than 10, it goes in the left. Otherwise, it goes in the right. Yeah, that's working. Oh, that feels weird. Oh. That hurts my brain a little bit. That's a very strange sensation. But we can do, dot odd. I wonder if this will feel weird. So we're going to check the harmonic number. If it's odd, it goes in the left. If not, it goes in the right. Odd not understood. Interesting. If the harmonic divided by, oh man, divided by 2. Well, there's a way to do this. Is odd? No, of course not. Modulus 2, yeah, that's a good way. Yeah, modulo 2 equals 0. Good call. Mod 1. No? Let's let me trace this pattern. I think we can. Do we need a pfunc? Yeah, okay. So we're a little bit out of my territory here. I'd have to goof around with this. Pfunc. No, the p key is a pattern. The harmonic. Let me just trace this. Why are you not tracing? Yeah. I'm actually very surprised that this is not working. It's even not understood. I think maybe pfunc, and we can pass in the event. Event at harmonic dot odd. Is that going to work? No? Okay, I'm going to give up on this. There's a way to do this, but I'm just goofing up the syntax. But we saw that pif works, right? It was just it's something weird with odd. Anyway, okay. Let's go back to B white. Yeah, sorry, David. The last thing I want to do, and then we'll call it a night, is how we can change patterns on the fly. We can use a pattern called Pdef n. We'll call this like, you know, mn for MIDI note. Call it whatever you like. So we've just wrapped Pdef n, wrapped 43 in a pattern. So now this is like MIDI def, synth def. So now down here we can say mn 45. Ah. And now we've sort of arrived in the territory of live coding. Right? The maximum polyphony of SuperCollider. Well, it depends on in what context you're talking about polyphony. If you're talking, I mean, there is something called, there is an attribute on the server called max nodes, which is 1024. Of course, this value can be changed if you want. And this means that once you have, if you try to add a node number 1025 to the server, I think it'll just throw back an error saying too many nodes or something. But Eric Zurban actually came in my office and we made 8,000 sine waves simultaneously, and you know we managed to get 8,000, and you know the server was struggling, but so I don't think there's technically a max polyphony. It kind of certainly not within SuperCollider. You can have as many as you want. I mean, here's a sine wave. So here's one voice. Here's another. So it's just a matter. I mean, there's really no limit. The limit is how much signal processing your computer can handle at one time. How many processes it can deal with. The volume is controlled here in this pattern. So I can, bring this up a little bit. Yeah. And you can wrap any pattern you like in Pdef n. Just make sure you give it a unique name if you want to treat it uniquely. And we could even, I mean, what do I call these? It's good to come up with a naming convention here. So I'll just call this pan control, and I'll call this MIDI note control. So now we can also change the panning on the fly. We can make the spatialization much more narrow. And if we set it to 0, then everything's pan center. And remember, if we use integers for p white, we're going to get integers. So now everything will either be panned hard left, hard right, or center. It's kind of an interesting effect. I don't know if you can run this on a mobile operating system. Yeah. I'm impressed too. You just like dropped into the chat and got some SuperCollider synthesis cooking. It's pretty cool. I don't know if there's a mobile version of SuperCollider. I don't think so. But it's Mac, Windows, and Linux, at least. Yeah, we could put distortion on it. You would start by building that into the SynthDef somehow. I don't know, this might sound kind of ugly, but we can do sig equals sig times 2. Let's do times 1 point. No, you know what? Let's make an argument. Clip amp dot clip between -1 and 1. So we'll start it at 1, so we're not going to have any sort of problems whatsoever. And let's make clip amp Pdef clip control 1. All right, so just to, I guess I'm going kind of fast here, but we've added a new line where we multiply the signal by some amount, which is initially 1, so no change, and then we clip it between -1 and 1. So we can ramp this up, and then we'll end up clipping our sine wave. And then here I've just added it to our Pbind as a new key, and it's wrapped in a Pdef, so we have a sort of real-time control. So let's see what happens. Hey. Yeah, so there's your distortion. Oh, that's cool. I didn't know. I wasn't aware that people were working on the mobile. Right. That is right. We have defined an instrument or a SynthDef called sine, which basically plays a sine wave and creates an envelope. It does a little optional distortion in this case. It applies the amplitude envelope and also has an overall amplitude argument, and then pans it in a stereo field and outputs it. That's our instrument definition. And then we have a pattern which generates synths using this SynthDef based on these parameters. So it's using this instrument. It's going to wait this much time between successive synths, and then we can also provide like MIDI note, harmonic, detune, and then amp and release, which are defined up here, pan, clip amp, etc. Right. I mean, if we're making note events, then our options here are determined by what we've declared up here. And in the case of Freak is a little bit special because it's got this hierarchy. So we don't have to, we can specify Freak directly, but in this case, I wanted to be able to specify a MIDI note and a harmonic of that fundamental. And there's this hierarchy down here, which I have to like undock it to see it all. So I'm providing MIDI note, harmonic, and detune. And you can work at this level, and you can work at that level. Can you live record any sound and take the spectral analysis and manipulate using this Pbind to be? I mean, probably, but it's yeah, you can do that. I think then now you're getting into the territory of the FFT stuff. So there's a whole bunch of FFT objects in SuperCollider, and you can do analysis. It's probably not the easiest thing in the world to do if you've never done it before. You might try to think of maybe a simpler way to do it, or do it in some program which is dedicated to that. And I don't know. It's a good question. It's a good question. It's looping indefinitely. Oh, I didn't even really talk about this. It's because all of the patterns are infinite. If we just have a single value, it's equivalent to this basically, or a pseq that just infinitely repeats the thing. So yeah, we can actually make this finite. That's a really good. Yeah, I just happen to make all these infinite. So let's go with duration, and instead of an infinite number of durations, let's just do 100. And once this Pxbrand outputs 100 values, it's going to start returning nil. And when we pass nil into one of these events, that basically puts a cap on all the other infinite patterns. Whenever anything returns nil, that's the end of the game. So let's go ahead and do this, and we'll trace these as well. No, it's not going to give us very much information, but we'll just make an arbitrary 1, 2, increase by 1. We'll make this infinite, and so we're going to trace this, and so we'll see these values. What did I do? What's wrong? Oh, I forgot a comma. I forgot my comma here. Okay. And that's it. Yeah, so if all of these patterns have an infinite length, then the Pbind will generate an infinite stream of synths. But if any of them is not finite, then that determines the length, the number of synths that the Pbind creates in that stream. So if we were to make, this pattern only 50, well, I don't know why it went to 51. Weird. Did it start it? Oh, I guess, right, because we started at 1. We started 0. Yeah. So now this is the shortest pattern. There are 2 finite patterns. It's this one and this one, but this one ends first. So that determines the length of the stream that produces the synths. But if they're all infinite, then it goes forever. I didn't know about the tuning library quark. It's quarks.gui. Yeah, there's a whole bunch of quarks here. Yeah, this one, tuning library. Yeah, all these quarks do crazy stuff. I am not as involved with the world of quarks as I maybe should be. I tend to stick to the vanilla, language. Okay, wow, it's past 10. So I know we covered a lot of stuff here. Its patterns are pretty deep, but I think the big takeaway I want you to have is this combo deal right here. You make a synth-def. Oh, the color diagram is at the bottom of the event help file. That is down here. So just do a help file search for event, capital E, and at the very bottom you have this colored diagram. Yeah, so this is, I want this to be the primary takeaway. I know we did a lot of stuff at the beginning with just, basic patterns and turning them into streams and then calling next. And that's actually a pretty useful way to use patterns. But the most common way patterns are used is with Pbind to generate a sequence, a stream of synths as note events. And then you can algorithmically control individual parameters of the synth-def being used using more patterns like Pwhite, Pxbrand, Pseries, whatever. All those patterns in document 2 in the practical guide. You can get so much done with just these, 10 or 15 patterns. Pseq, Prand, Pxrand. It's just, it's really, really quite flexible. Just these basic patterns. Of course, there's hundreds more patterns, most of which I've never used. But this is the takeaway here. Make a synth-def and play a Pbind using that synth-def. And I think that'll be the focus of the in-class assignment as well as the take-home assignment you guys will get tomorrow. Oh, okay. I don't know, David, about the quark. You should ask Alan, because I think Alan probably knows more about quarks than I do. Thank you, Meat Goat. Thanks for stopping by. Glad you liked it. Hey, Beetle. Oh man. All right, so please watch, if you're coming to class tomorrow, watch the tutorial 10 on my YouTube channel. I have not been making the homeworks available online, partly because sometimes not everyone turns them in on time, and then if they're online, you can, I don't know. I'm just I might make them available like at the end of the semester, or I don't know. I'll think about it. I mean, it's a good idea. I mean, the thing is, if I put the homeworks online for everyone to look at, then it is. But I mean, I totally acknowledge that by doing a live lecture that's like publicly available, that I get non-students, and I encourage that. I'm not trying to keep people out. I mean, it's kind of the point of doing it like this. The thing is, if I put the homeworks online, I assume people would also want the answers. So I'd have to put those online as well. And it just makes things a little bit complicated. But I think even once the semester's over, if I offer this class again, I don't really want the homework and answer keys floating around, because then I'd have to like rewrite them every time I offer the class. But if you want to send me a private message, I could just like send them to you directly. If you're really interested, I'd be happy to do it. Okay, so that's it for patterns. There's more to talk about, but I think this will hopefully provide a decent introduction to the basic value patterns as well as Pbind and how it can be used to generate a very complex sequence of sound with relatively simple code. So yeah, watch the tutorial and do take a look at the 2 guides that I pointed out in the beginning. Next lecture is going to be a week from now. I do this semester, it's every Wednesday at 8 p.m. Central US time. So 2 hours previous from right now is when I start. So whatever time it is for you, just rewind by 2 hours and 10 minutes. And that's where I'll be next week, same time. And next week, we are talking, I think, did I get that right? Let me look up the syllabus real quick. Syllabus. What is next week? It's GUI, graphical user interface design, and boy oh boy is that fun. GUI is great. It's and then next week open sound control, and that'll be a lot of fun. So we're kind of closing in on the end of the semester here. I'm gonna, hey Kramer. I'm gonna ask. I think I'm gonna give everyone a week to submit your final project proposals. So just a general sense of what you're gonna do, and in exchange, I'm gonna come in tomorrow, or maybe upload to Compass a bunch of examples of what you might do for your final project. Like I have a short composition that I made before I really knew what the hell I was doing in SuperCollider, to give you a sense of, it's just something that you can theoretically put together in about 4 or 5 weeks. So we'll get on that final project schedule and lighten the load a little bit on the in-class and take-home assignments. But we are going to dive into some patterns this week, and then we'll dive into some graphical user interface stuff next week. Okay. So that's it. That's it for this week. I'll see everyone who's taken the class tomorrow afternoon, and I'll see everyone next week. Same time next week, and we'll talk about graphical user interface design. It's going to be a lot of fun. So thank you all for watching. And see you all next time.